It's a common observation in any large system. A critical piece of information exists somewhere inside of it. Yet, somehow, between its point of origin and the decision maker who needs it most, that information gets lost. Now, this isn't an accident. It's the predictable, even structural outcome of the system's own growth.
And this reveals a central paradox of scale. The expectation is that adding more parts to a system, more nodes, should improve its ability to process information. But the reality is often the exact opposite. As a system grows, the information flowing within it tends to become fragmented, distorted, and even lost. So, to understand why this happens, we need to start by looking at a system in its simplest, most ideal form.
So let's begin by modeling a system at its smallest possible scale. This is a state where the relationship between its parts and the information they share is perfectly clear and direct.
So, what is a system? Well, fundamentally, it's a set of interconnected components that, together, produce their own pattern of behavior over time. The key things to focus on here are the components themselves, the connections between them, and the overall behavior that emerges from all that interaction.
In a small, simple system, every component, we'll call them nodes, can connect directly to every other node. All of the communication pathways are completely open.
This direct connection means information gets transmitted with very high fidelity. The message sent is pretty much the message received. There are no layers of summary or interpretation to degrade the signal. You could call this the system in its perfect, frictionless state.
However, no system really exists in a vacuum. It's always subject to internal and external pressures that compel it to grow, to add more components, and manage more complexity. This is the pressure of scale.
As you add more nodes, the number of potential connections doesn't just grow linearly, it explodes exponentially. For example, a system with just 4 nodes has 6 connections, but a system with 10 nodes has 45, and a system with 100 nodes has nearly 5,000 potential links.
This exponential growth in connections will inevitably lead to something called information overload. The volume of incoming information simply surpasses the system's ability to process it effectively, and that, in turn, leads to a degradation in the quality of its decisions and its outputs.
This state of overload happens because the pressure of scale activates 2 fundamental and really inescapable constraints that are just inherent to any information system. The first limitation exists inside each individual node. Every component, whether it's a person or a computer processor, has a finite working memory and a limited capacity to process information. This concept is often called cognitive load. So when the amount of information coming at a node exceeds its processing capacity, that extra information isn't just put in a queue. It gets filtered, it gets misinterpreted, or it simply gets dropped. The node becomes saturated.
The second limitation doesn't exist in the nodes themselves, but in the connections between them. You see, every communication channel, which is the medium that a message is sent through, is subject to interference, or what we call noise. Now, noise can be anything that distorts the signal. Ambiguous language, technical glitches, even cultural misinterpretation. Because of noise, the message that's received is never a perfect one-to-one copy of the message that was sent. So faced with systemic failure from this information overload, the system has to adapt if it's going to survive. This adaptation isn't something designed by a single person. It emerges as a rational response to the constraints of node and link limitations. That fully connected model, which was once a source of strength in a small system, now becomes a critical vulnerability at scale. The sheer volume of communication creates a kind of system-wide paralysis. Maintaining every single potential link is just no longer sustainable.
To manage all this new complexity, the system begins to self-organize. It starts shedding connections, and a new, more efficient structure emerges, a hierarchy. This structure dramatically reduces communication overhead by limiting the flow of information to only the most essential pathways.
In a hierarchy, information doesn't flow directly between all the nodes anymore. Instead, information at a lower level gets aggregated and summarized. That summary is then passed to the next level up, where the exact same process is repeated. This is what makes the huge amount of information manageable.
But this elegant and completely rational adaptation, well, it contains a fundamental trade-off. The very mechanism that allows the system to function at scale is also the very mechanism that guarantees information will be lost.
Think about it. The process of summarization is, by its very definition, a process of deletion. To make information concise enough to pass up the hierarchy, you have to strip away nuance,
context, and raw data. So the system gains efficiency, but at the direct cost of information fidelity.
This really illustrates the core trade-off. A small system has that high-fidelity information, but it's not very efficient. A large system, on the other hand, gains massive efficiency, but only by sacrificing that fidelity. At scale, one is achieved at the expense of the other.
And it's critical to understand that this outcome isn't the result of faulty components or some individual's error. It isn't a mistake that you can just correct with better training or flashier technology. It's a structural inevitability.
Information loss, therefore, is an emergent property of the system itself. It's a predictable, structural outcome that arises from rational actors all working within the dual constraints of cognitive load and channel noise. So the paradox is resolved. A system doesn't lose information despite its growth. It loses information because of it. It's not a bug, it's a feature of scale itself.